Use the definition of multiplication discussed in this section to explain why both of the following equations model the problem of determining how many squares make the rectangle in this figure 4.8. For each equation, state clearly what one group is and explain how you are viewing the small squares as organized into equal groups. Okay, let's take our figure. Two equations. And let's focus on the definition of multiplication. So myself a little space where A is the number of groups, B is the number of items per group, and then C is the total number of items. Okay, just in a most general way of speaking about it. Okay, so let's take a look. We have 6 groups of 9 squares for our first expression. So here we will need 6 groups of 9 squares per group. And that's going to be in the shape of the rows. Right, so we'll have 1, 2, 3, 4, 5, 6 rows. Each with right 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And we can show our row count since we're labeling. Okay, so 6 rows, each with 9 squares per row. And then that same image, right, because we just copy and pasted it, is 9 groups. Let's take our black. On this one, we have 9 groups of 6 squares per group. So we will this time we'll go for columns, right? So 2, same counting. We'll have 1 through 9 across the top and 1 through 6 going down. But this time we're grouping the columns. Okay, so this time we have 1, 2, you know where I'm going with this. Nine columns. With each with 6 squares in each column. Okay, so we've used our definition of multiplication to describe how each of these equations represented the array to begin with, right? So each of these equations is valid depending on which image you provide. Okay, let's go ahead and save this. Okay, write a multiplicative comparison word problem for 3 times 5. Draw a strip diagram for your problem in part A and explain how this section's definition of multiplication applies to the problem. And then in part C, reword your problem in part A so that it is about the same situation, but you use the fraction 1/3 in the statement of the problem. Okay, so let's first think about the definition of multiplication. So we have the definition of multiplication being A times B equals C, where A is the number of groups, B is the number of units per group, and C is the number of units. If we have a multiplicative comparison problem, then one individual will have B items, for example, and then another individual will have A times as many as person who has B items. Okay, so when we draw this, we will have an amount and we will have to have 3 times that amount for the second individual because those are our numbers. So 3 times that's going to fit our definition of 3 times 5. If we have 5 in each of these groups. Okay, so I'm going to darken this. And we could have used numbers here, right? We used more of a number line looking strip diagram, but we could have also just stuck a 5 inside of the box. Okay, so what we have here is, well, we first have to write a question. Okay, so let's see. Dar has 3 times as much driving time as Eliza. Eliza has 5 hours of driving time. Let's see. Already have run out of space. How much driving time, because you have to remember to actually ask the question, does Dar have? Okay, now that we have individuals that we can put labels onto these strips for, we have an amount for Eliza, which we know is 5 hours. And we have 3 times that for Dar. And as a result, the question for how much drive time does Dar have, that would have been our question mark location. The answer being 3 of these parts, right? 3 groups. And we should label that hours. 3 groups of 5 hours per, for lack of a better word, groups, right? 3 parts of 5 hours per part, 3 compartments of 5 hours per compartment, right? However you want to word that, box, square, right? Strip of the strip diagram, for example. But as a result, we do have 3 times 5, which here we see, especially when we drew it out individually, is 15 hours. And we always have to answer in question answer form. Dar has 15 hours. Okay, now what we have in part C is the challenge of rewording our problem so that it's about the same situation, but you use the fraction 1/3 in the statement of the problem. So we could say that Eliza has 1/3 of the hours that Dar has, and then say the rest of what we have. So let's alter and say Eliza has 1/3 of the driving time that Dar has. That replaces our first sentence. And then everything else is the same. Eliza has 5 hours of driving. How much driving time does Dar have? Same scenario, same drawing, but we're using the fraction 1/3 instead of 3. Okay, let's talk about multiplying by 10. 10 times 23 is 10 groups of 23, right? So using the definition of multiplication, we have 10 groups of 23. We're going to use base 10 shorthand. So base 10 shorthand. And the key will be such that the unit is worth 1. The rod, which is 10 units, is worth 10. And then the flat, which is 10 rods, is equal to 100. Now, we are asked to illustrate using 10 groups of 23 to show why we move the digits in the number one place to the left when we multiply by 10. So let's look at what they mean. So to the left, this being the right, this being, sorry, the left. Okay, so when we have the 23 here and we multiply by 10, they're saying these digits move to the left, becoming 2, 3, and then a 0 here, right? So that's what they're asking us to show is how does 230 become, sorry, how does 23 become 230 in a visual display? Okay, so we are going to use base 10, right? And for starters, what does 23 look like, right? So 23 is, make sure I do this with enough space. 1, 2 of the 10s, and then we do a better job than that. And then 3 of the 1s. And now what 10 groups of 23 is 10 of those, right? That's the group. So we will write 10 of those. So there's 1, bear with me. Put 1 up here, so I have enough room. So that's 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 groups of 23. 10 groups of 23. 10 times 23. Now, because we've stacked it like this, then what we can do is we can make groups of 10 and regroup it as a next image, right? So we regroup and redraw. So I'm going to start with my 1s. And let's see. Here's 10 1s. So that will regroup as a rod. Then I have another 10 units that regroups as a rod. And I have another 10 units that regroups as a rod. And now I'm going to use a different color. Maybe we can see it a little better. I'm going to regroup 10 rods and trade it out for a flat, right? So I'm going to take a group of 10 rods and trade it for a flat. And then another group of 10 rods and trade it out for a flat. And as a result, we have 2 flats and 3, scared me, and 3 rods, right? And that 10 groups of 23, when regrouped and renamed an image, becomes 2 of our hundreds plus 3 of our tens and none of the original ones, right? So kind of ran out of space over there, but no ones, right? So that's how we end up getting 230. So our final image has the value 230, which is what they were describing. 23, when multiplied by 10, shifts the digits in the number 1 place to the left when multiplying by 10. So That was a section 4.2 problem. And this is what section 4.2 is about, multiplying by 10. Okay, 4.3. Suppose you have 60 pennies arranged into 12 stacks with 5 pennies in each stack. The 12 stacks are arranged in 3 rows with 4 stacks in each row, as shown in figure 4.21. For each of the following expressions, explain how to see the pennies grouped in that way. Your explanation of the grouping should not involve rearranging the pennies. Okay, so that means each one of those expressions will be about the same stack. So we'll just draw this stack 4 times and then look at the different ways to talk about them. Okay, so we have here 3 groups of 20 to start. So 3 groups of 20. And the 3 groups are here. So we see 3 groups. So 3 rows. And then we have to look at what 4 times 5 means, right? 4 groups of 5. So each stack is a group within a group, right? So what we have for 3 times parentheses 4 times 5 is we have 3 rows of 4 stacks of 5 pennies. So we have 3 rows of 4 stacks per row, each row with 5 pennies, or each stack with 5 pennies. So 3 rows of 4 stacks of 5 pennies in each stack. Okay, so we didn't rearrange the numbers and we kept with the 4 groups of 5 and 3 groups of 4 times 5. Okay, in the next one, B, we have 12 groups of 5 to start with. So to get us started, we need 12 groups of 5. The 5 is going to be the pennies in each. So this time around, our 12 groups are the stacks themselves, right? So again, we need to look at what 3 groups of 4 means, right? So we have 3 groups of 4 groups of 5. So this is 3 rows let's see. How am I wording this differently? Right? It's it's a kind of almost worded the same. 3 rows of 4 stacks. Three rows of 4 stacks. Giving us 12 stacks. And then each stack has 5 pennies. So this first one, then 3 rows. Each with, I guess, to try to differentiate, right? Each with 4 stacks of 5 pennies, making 20 pennies each. Okay, so this one here is a little harder to circle just because we're going to have 12 groups. I don't know if they ever meant for us to circle them, but we have 12 groups. The groups themselves being made of these rows and columns type of thing. Okay, so let's look at 5 times 3 times 4. So this will be 5 groups of 3 times 4, right? So the pennies are in 5 layers. Each row, right? Because then we have a 3 times 4. So each layer has 3 rows and 4 pennies in each row. That's awkward. Okay, so this is a, let's see, that's a row. Okay, so each penny has a layer. So there's a layer, and then because there's 5 pennies, so oh, I need space. That's part of my problem. All right, I'm gonna move it up a little. Okay, so pennies are arranged in 5 layers. And then each layer has 3 groups of 4. So 3 rows. So that being our top layer. If we were just looking at one stack, right, then the top layer, and then we count all of the top layer, and then the second one down in the stack, we count all of that layer. It's weird. I don't like it, right? But what we have is each layer has three rows of 4 pennies. So there are 12 pennies in each layer, right? It's weird. But that's what we have, right? So the layer itself is the group. And then we have 3 rows and 4 pennies in each row for part C. Part D, let's see if we can get this one. 4 times 3 times 5. 4 is the stacks. So we'll have 4 stacks. And then I'm thinking, or 4 columns. There we go. 4 columns. Each column has a set of 3 stacks, and each stack has 5 pennies. I don't mind this one. The hardest one for me was C. That was awkward. Okay, let's look at D. D's back to something like A. So 1, 2, 3, 4 columns, right? Let's see. So for D, oh, scoot it up a little, give myself, well, maybe me scoot up a little. Okay, so for D, I have 4 columns, each with 3 stacks with 5 pennies per stack. So the only thing we didn't do in D and A that we did in B and C was articulate the multiplication. We said it, we just didn't write it, right? So in D, then we have each with 3 stacks of 15 pennies per stack, giving 15 pennies in each column, right? Something like that. That way we can tell the number of groups is the column, and then we broke down what the 15 was, but then we also gave the 15 so that it's 4 times 15, but also it's 4 times 3 times 5, right? And let's finish out the blue one as well. So in the blue one, we had 3 rows, each with 4 stacks of 5 pennies, which is 3 rows of 20 pennies, right? Okay, so what we did was we take the same stack of pennies. We didn't rearrange the pennies, we left them. We just counted them differently, right? So one time we counted them horizontally, one time we counted them vertically, one time we just sliced off the top and counted the top, and then pushed all the top off, counted the second, pushed all the second off, counted the third layer, right? And so we counted this same amount of pennies 4 different ways. And those ways involved the commutative property and the associative property. So let's clear this out and write the properties down. C was definitely the most difficult for me. But lean into the definition of multiplication, right? Where we have 2 factors. The first factor is the number of groups. The second factor is the number of items per group. Okay, so what we want to express now is the commutative property and the associative property. So A times B has the same value as B times A. We see, let's see. Let's write, I was trying to see if we see one easily here. But I see more commutative properties, so let's try that. Oh, that one's commutative. I see more associative. Okay, and then this one, A times B times C and A times B times C. So we have A times B times C, or A times the product of B times C. So this one is our associative property. Okay, that's the one I was looking for a second ago, I think. But let's see. We've got 3, 4, 5 for A and 3, 4, 5 for B. So let's look at that. That one on number B is written 3 times 4 in parentheses times 5. And on A, it's written 3 times 4 times 5. So between A and B, we've used the associative property, where we've just moved what we're grouping to a different group first, right? So, and even in the definition of multiplication, we have 3 groups of 20 versus 3 times 4 groups of 5, right? So that didn't come out very well, but 3 groups of 4 times 5 versus 3 times 4 groups of 5 barely came out better. Okay, let's see. And then in between C and D, then we can see some commutative property, right? Where a term actually physically moves. Here we have, let's see, 3, 4, 5. Let's look at between B and C. So in B, we have 3 times 4 times 5. And in C, we've moved the 5 to the front, and we've moved the group to the back, right? So just in terms of pure numbers, right? So there we've used between B and C, we've used the commutative property. So we have examples here of the commutative property. Usually a place we see it a lot of the time is with area, where we'll talk about length times width being the same as width times length, right? So it doesn't matter generally to us if we're taking length times a width or a width times a length, right? We look in terms of arrays to help us explain, right? So for example, this could be 5 columns of 3 squares per column. And that has the same value. It's the exact same rectangle as looking at 3 rows, each with 5 squares per row. So whether we look at L times W or W times L, those produce the same amount of squares. It produces 15 squares here in our example. And a place we see the associative property then is with volume, length times width times height, length times width times height. So if you look at your room, then you can take the area of the floor and stack it to the ceiling to fill the room, right? So volume that way, take the area of the floor, stack it to the ceiling. Or you can take the area of the wall and stack it out the distance of the room. And that will also fill the room with volume, right? So here in this one, we group the area of the wall and then we stack it times L to the, or across the room. Let me erase that a little. We stack it through the room to other wall, something like that. You get my gist though, right? So across the room to the other side. And that's volume, right? Which, you know, you don't want to see me draw a cube, but here goes. Nope. Sorry. Terrible, terrible cube. Okay. Removing something, you're commuting. So think of the root word commute. You physically go from Berlin to Albuquerque versus associative. property where you're just associating the W here with a different term first. Well, here factors, right? So we want to find the product of L and W first versus finding the product of H and W first. All right, write equations to show the commutative and associative properties of multiplication to show how they are involved when you calculate 40 times 800 mentally by relying on basic multiplication facts, such as 4 times 8. Write your equations in the form of 40 times 800 equaling some expression, which equals another expression, which equals another expression, which is your answer. Indicate specifically where the commutative and associative properties of multiplication are used. Okay, so we are going to remind ourselves what the rules look like. So we have A times B times C, right? And you can move a term or you can reassociate. And really, these aren't terms, they're factors, right? So A times B grouped, then times C, or B times C grouped, then times A, right? So it looks like the grouping of A times B times C then is the same as A times the grouping of B times C, right? This is our associative property. And the commutative is to physically switch places. So to convert one position for another. So here is our commutative property. And if we were to multiply 40 times 800, just talk it out, I would probably multiply the 4 times the 8 as they suggested and get 32. And then I would quote unquote add 3 zeros. But you're not adding at all. So you have to be careful when you say things like that, right? So we're really putting 3 zeros onto the end of our number, which is the right side of our number. Okay, so what we did though was 40 times 800. I first had to split it into 4 times 10 times 8 times 10 times 10 in my head. Maybe I left it 100. I don't really know. And then I moved the 8 and this 10, right? So I'm going to wait a second and now move these two so that here in this next equal sign, I've used the commutative property. So to make the next equal sign true, I use the commutative property. Now I'm going to associate, oops, the 4 with this 8, and then all of these 10s together, right? So it's technical here because I suppose right here we've used the associative property because we didn't group any of the 10s with the 4 and the 8. We grouped them all very specifically with each other. Otherwise, we should just be multiplying from left to right. And so in my brain, I said 32 times 1,000, right? That's where I got the 3 zeros that I tacked on to the end. And then 3, 2, and 3 zeros. So this is what they mean, or some version of what they mean, when they ask us to start with the expression they gave us, have an equal sign, and then start to break down the expression, keeping our equal signs in order, and then ending with our expression, right? And I maybe didn't need to break this all the way down, right? But that's fine. And let's see. Did I have anything else to add? Not that I can think of, I guess. Might have interrupted my own train of thought there, but indicates specifically where we use the commutative, associative. We started at the start, we ended at the end, and we have equal signs connecting each expression along the way, right? And we also included the properties themselves, which always adds to the conversation and doesn't take away from it. Explain how to make the following product easy to calculate mentally. There are 5 2s and 5 5s in the product. So I probably would pair each one together. I think that's what I would end up doing, so that I had 2 times 5, and then I would have 2 times 5 a certain amount of times, right? So let's take a look at that. So one thing I've done is simultaneously moved positions and reassociated my multiplication, right? I've inserted a 5 forward. And now what I have is 1, 2, 3, 4, 5. Well, they told us we'd have that, but we have 5 groups of this quantity that's 2 times 5, right? And so as a result, we have 5 times 10, which is quite easy to calculate.